All right, let's do and take a look at the homework, page 251 in your textbooks. You did number 1H or B and 1H. And before we take a look at the homework, though, let's review our most recent conic, Quentin, which is the hyperbola. And every one of our conics we've defined as a locus in some way, right? We define it either as a locus of points given distance from given point, right, which was the circle. We had equidistant from a point and a line. Parabola. We had the sum of the distances from two fixed points is constant. And then now we have the difference of distances from two fixed points is constant, and that's the hyperbola. So we've got two fixed points called the foci, and the difference of the distances from those 2 points always remains the same in a hyperbola. Now the hyperbola looks really different from all the other conics. The most notable difference is it has two different branches to it. It's not one curve, it's actually two curves. Now, I use the term curve loosely, right? As we saw in the homework with those that were rather ugly, the curvature was not particularly great. You're looking there on page 251. There's some pictures, by the way, of hyperbolas or hyperbolic paths. And if you look at the recoil and deflection here, you notice the deflections, you see a couple deflections of helium ions as they go through very thin gold. And you see a couple of them are really, they almost look flat, don't they? Some of them are straight through, and there's a couple deflections. The recoil is a really sharp curve. But all of those hyperbolas, right? So the hyperbola can have a really sharp curve. It can have a moderate curve like we see in the first typical hyperbolic path, and then we have the more less pronounced deflections as well. Again, the hyperbola's got a lot of range of curvature to it. Also, we said the hyperbola is the only conic that has... That's true, in the conic form. That's a really vague question. I was looking for asymptotes, but as I asked the question, that's a really vague way to ask it. It's the only conic that has asymptotes in the graph. Now, to the conic form, the defining characteristic is the fact that you got a minus sign where?
Between the x squared and the y squared.
Right. One of the squared variables has to be a negative for a hyperbola. All the others are positives on the squares. Right? Now, you might be missing a square in the case of the parabola. You might have different numbers in front of the squares for the ellipse, but at least they're added. They're always added, always positive. The only time one of the squares will be negative, and only one, of course, will be for the hyperbola. What is that hyperbolic form that we're looking for here?
X squared over a squared minus y squared over b squared equals 1.
Good, and if it happened that the x were negative and the y were positive, then this wouldn't be a squared anymore, it'd be b. Should have left the squared. And then this would be a squared. Laziness lives. Right, so the a squared, remember, goes under the positive one of those. Now on the hyperbola itself, as we go to graph it, technically a hyperbola is symmetric to both axes. But wherever the foci lie, right, again, those are the 2 points that define the hyperbola. That line that runs through the foci is the main axis we will use. Along that main axis, you'll find a couple of vertices. Remember, the foci lie outside the vertices here, and specifically this length between the vertices is called the transverse axis. Remember, trans refers to going across or going between, like transatlantic or goes across the Atlantic. So transverse axis runs between the two V's, or V and V prime, I should say. The midpoint of the transverse axis is what we call the, well, because it's not part of or even within, we don't call it the center, but the origin of the hyperbola. And for now, the origin really is at the origin. Today, we'll start moving that around. And then the perpendicular bisector here is not the transverse axis, but the conjugate axis. Now, technically, it's not the whole line. It's got a predefined length to it. And, of course, we said we'll just mark these with little lines there because the points themselves don't matter. And really, the purpose of the conjugate and transverse axes from a graphing perspective is so we can simply get the the fundamental rectangle of the hyperbola. And that really, for our graphing purposes, we don't even really care so much about the fundamental rectangle as much as we just do the four corners of the rectangle, because it's those four corners that define our asymptotes. And so the asymptotes, remember, very important to getting a good conic. Now, through the foci, perpendicular to the main axis we use, again, this is technically the transverse axis, but if we think of the thing as like the extension of the transverse axis, perhaps. Perpendicular there, we have perpendicular focal chords, still called the
lattice rectums.
the lattice rectums. Latera recta. What is it?
The latera recta.
Latera recta. And we'll be given the length of the latera recta here. Again, normally we'll just locate the endpoints thereof. And of course, that'll be true on both sides here. And remember, the key is to go through the ends of the latera recta, approaching but not touching the asymptote. And curving it, just a little bit of curvature here, approaching but not touching the asymptote. Not a nosedive hard into it, not running parallel, not running away from it, but just going toward it. And that makes the graph loads of fun. And something like that is what we'd be going for. In this case, obviously the main axis, or the extended transverse axis, is the x-axis. And how would I tell from the hyperbolic form that it is going to be the x that is the transverse axis?
It will be positive.
The x squared will be the positive ratio. The y squared will have your negative ratio on it. Also, the length of the transverse axis algebraically could be represented 2a. Remember, 2a is the length of the transverse axis. This length of the conjugate axis would be represented, or not. And then from O to F prime and O to F, from origin to foci, we refer to that as our focal length, and it's going to be represented by the letter C. How do I find C? Go square root of a squared plus b squared. Okay, so there's a notable difference with the ellipse where it's a squared minus b squared. Obviously then the focal length C is going to be bigger than a, but the ratio of C to a is still the ratio that defines our the ratio of C to a, focal length to half transverse axis, is our eccentricity. Remember, it's the same ratio for eccentricity we had for the ellipse. It's just C was always smaller than A for the ellipse. If C is bigger than A, then it's the hyperbola, which means E always falls between what values?
1 and infinity.
Good, 1 and infinity. So basically bigger than 1 for the eccentricity. Now, speaking of the lattice rectum, we said normally we'll look at just half the lattice rectum, and we don't have a letter for it necessarily, but how do we find the half lattice rectum length?
B squared over A.
B squared over A. If you were looking for the entire length of the lattice rectum, it's 2b squared over A. Same thing as for the ellipse as well. Let's see, I think that is everything we needed to review, so let's take a look at the homework. Page 251, number 1b. And what's the original problem they gave us here, Quentin?
9x squared minus y squared equals 9.
9x squared minus y squared equals 9 for 1b. All right, first key, like the ellipse, same thing with the hyperbola and the hyperbolic form, got to set the equation equal to 1. So do that.
8 squared over 1 minus 9 squared over 9 equals 1.
There we go, just divide everything by 9. Exact same thing we did for the ellipse. And so our first thing, unlike the last where we'll find the center of the ellipse, we'll find the origin, a similar idea though.
0, 0.
And for now it will be 0, 0. Again, in just a few minutes we'll translate it. And then we're not looking for a major axis, but rather the transverse axis lies along which? The x, because again, it's got the positive. We're not looking for what's bigger. Transverse doesn't have to be bigger. Major has to be bigger than minor. Transverse could be whatever. We're going to choose to make the transverse axis our x-axis because it's got the positive here. And then we want the length of the transverse axis. Remember, this denominator of the positive is a squared. The transverse axis is 1 on each side because it's a and a, 2 total, right? But for practical purposes, it's easier to think in terms of 1 each. The conjugate axis, 3 each. Again, this is b squared, so b is 3. You could say it's a total length of 6 for the conjugate axis, but again, it's best to think in terms of each. For the focal length, remember, that's the square root of a squared plus b squared. If I add those two squares, I get 10, so we'll take the square root of 10, and that'll give us approximately 3.2 for our focal length. And then finally, the half latera recta, b squared over a. Well, remember, this is b squared. A is 1, and oh my goodness, the halves of the latera recta are going to be 9. So the whole lattice rectum length is 18 through each focal point. So very long latera rectum, which means a very flat hyperbola, I'm afraid. Let's take a look at the graph here. And I hope my graph is, let's see, x is transverse, which means if x is transverse, the latera recta are going to go up and down. So I need to make sure the graph is plenty tall. I don't need it to be super deep this way, but I need to be really tall. So I'm going to use the full length of my Cartesian plane to make sure I've got room for what needs to be accomplished here. And I really don't need to bother too much with the x-axis because there's not a lot going to be happening there. 3, 6, 3, 6, 9, good. Negative 3, negative 6, negative 3, negative 6, negative 9, good. Now you understand, if this were not at the origin, if it were shifted up and down, I'd have to make sure I account for that, especially with long latera recta. So I'd have to, maybe shift the x-axis, accordingly. If it's a tall one, obviously side to side if it's a wide hyperbola. So we'll start at the origin, 0, 0, and you should have done that in the homework, and then on just one in each direction to the ends of the transverse axis. Again, the ends of the transverse axis are our vertices. The ends of the transverse axis are the vertices. Okay, so there's the origin, there's the vertices. Let me zoom in just a little bit more here on the graph, and hopefully that'll help it to be very clear. All right, then the conjugate axis, we're going to go up and down 3, and I'll just do a little bit of a line right here and right here, because again, all I really care about are the corners of the rectangle. Very tall, skinny. It's a 2 by 6 rectangle. But again, really the only reason I care about those corners is so I can get the asymptotes. And so we'll by the way, I was pointing out a moment ago that the recoil of the helium particle had a really sharp curvature. Imagine if the hyperbola was in here. It'd be very sharp, but because it's here, it's very flattened, okay? And how would you change that? Make this negative and that positive, and instantly it changes. Instead of, you still have the same shape of rectangle, it's just this way now. All right, so the foci, 3.2 along that x-axis. So remember, the 3.2 doesn't start at the vertices, but at the origin. 1, 2, 3.2, 1, 2, 3.2, and there's focus, the other focus. And here's another mistake students will make with the latera recta is they'll try to go off the vertex. No, we don't go off from the vertex, it's focal chords. So from here all the way up 9, very close to the asymptote, and down -9, again, very close to the asymptote. Same thing up here, and down here. And the fun part is to gradually curve like that. Erase the stuff you decided you didn't need. something like that. Again, not much of a curve at all. And then starting here, coming through there, retrace. It's almost parallel. It's close. There, it's getting closer. And sometimes you gotta do what you gotta do. I really do not enjoy graphing the long ones for this reason, but there we go. There's our hyperbola. Questions on the first one? All right, let's take a look at the next one then. Letter H, and we had negative x squared positive 4y squared is equal to 16. All right, same thing. First step is to set it equal to 1.
So negative x squared over 16 plus y squared over 4 equals 1.
Perfect. All right, once again, the origin,
0, 0,
the transverse axis.
y axis.
Again, it's positive. Now, I'll be honest, I like the big number to be transverse for this reason. You get a lot better curvature if the big number is transverse. But once again, the little number is transverse, which is just annoying. And you said how big?
2 each.
Total length 4. The conjugate axis?
4 each.
4 each, so total length
8.
8. Focal length?
Square root of 20.
Square root of 20, so let's see, that's got to be about
2.5.
2 or
4.5.
I was going to say 2.5, 4.5. All right, and then the half ladder recta.
8.
B squared, 16 over A, which is only 2, is 8. So not as bad as the last one, but pretty close. This time, though, the y-axis is transverse, which means our hyperbola is going to go side to side. So I need to make sure I have plenty of room side to side, not up and down. All right, so let's take a look. By the way, Jamie, do hope you get to feeling better soon. Quentin is missing you today as he has to answer all the questions. Well, he claims he's not bitter. I also heard something about she better be careful next pizza day when she goes to eat her pizza. So anyway, just take the warning for what it's worth. All right, let's go and take a look. So we start by plotting our
Origin.
at
0, 0.
0, 0. From there along the,
Y axis.
we're going to go up and down,
2.
and these are our
Vertices.
vertices. Good. We're going to go outward from the origin,
4.
4 in each direction. These are not points of consequence. These are simply at sides of the fundamental rectangle. And so once we've got these 4 points plotted, we kind of picture that rectangle and mark the 4 corners, so that we can then draw our asymptotes. By the way, is it ever possible the fundamental rectangle could be a square?
Yes.
Yeah, absolutely. Transverse and conjugate axis are the same length, and that's possible, right? It's not possible for major and minor axes to be the same length. Otherwise, you have a circle, not an ellipse. But it is possible for conjugate and transverse axes to be the same. All right, going back to the y-axis, starting from the origin, we're going to go up and down 4.5 to our, oh, that's 3.5, 4.5 to our foci, 4.5 to the foci, and then through the foci, perpendicular to that transverse axis extended, we're going to go outward 8 in each direction. And that's going to take us, again, pretty close to our asymptotes. If they're close to the asymptotes, it makes it flatter. Now remember, when we draw, we're going to go through the ends of the ladder erecta, starting at the vertices. If I had a student who's like, I don't get it, Mr. Jasky, it's flat. No, that's the focus. That's the ladder erecta. But also, we're not starting here. Like that wouldn't be much. I've had students try to start at the origin. No, start at the vertex. Curve your way through a little bit. Ooh, that side turned out really good. Other side, not as much. But that side turned out good. And here's where it would have helped if the line had been a little bit longer, because I could have kept going a little bit more there. So if you know you've got long ladder erecta, draw the sides of the fundamental, or the asymptotes. Draw the asymptotes nice and long. And kind of a little carried away there, but close enough. I think you can tell what it's supposed to look like. I'm not a perfectionist or anything. Okay, I'm a perfectionist. I'm just not perfect is the problem, and that is really hard. Nope. Okay, we'll call that good. And that's what we should have had. Now, Quentin, as I look at yours, I noticed you had to turn your paper sideways because you got going the wrong direction. Other than that, questions. Make sure you pay attention to which one is transverse, right? Otherwise, it seems like we did pretty well. All right, I want you to do number 1F now. There at your seats. Number 1F. Page 251, number 1F. squeaking as much as I can. You won't look that. Jamie's like, it's okay, Quentin. I was cringing for you. All right. I will say less is more in this particular instance. With your hyperbola, let's take a look and see how we did. All right, Quentin, letter F. When you divided everything by 100, you got? Now, I told you I like the ones where the bigger numbers under is the positive, because it's going to give you a much more curved hyperbola, and wow, a huge difference here. So this is going to be a very tight curve for a hyperbola, but the origin is still going to be at 0, 0. This time the transverse axis, which means the hyperbola is going to go up and down as opposed to side to side. The length of the transverse axis, 5 each, total of 10. The length of the conjugate axis, only 2 each, total of 4. The focal length,
5.4.
Yeah, square root of 29, which is about 5.4. So again, if you're comparing C to A, 5.4 to 5 is just barely bigger than 1. This is a very low eccentricity for a hyperbola. And then the half ladder erecta,
0.8.
yeah, again, very, very short. B squared over A, 4/5, which is 0.8. Very, very tight hyperbola. Going to look very parabolic as opposed to hyperbolic. So we started, of course, at 0, 0, and then assume along the y-axis you went up to 5, down to 5, and these were your vertices. Over 2 in each direction. So right, here's a corner, there's a corner, and there's a corner. And you made your asymptotes. All right, your foci at 5.4, so just about half a box past the vertices, and then out, not quite an entire box. So just these little triangles of dots here. So again, the key is to curve, approach but don't touch, curve and approach but don't touch. Curve, approach, but don't touch. And somehow this isn't looking very good. Something like that-ish. Though one side is drawn considerably longer than the other, so I'll make it look more aesthetically pleasing and do something like that. All right, and there we go. Again, it almost looks like 2 parabolas because it's tight enough this time. Questions on this? Again, don't try getting too far out here, and follow that curvature, and once you start getting close, just stop. Less is more. Questions on F? All right, well, let's take a look then at a translated origin. Why did I erase that? Oh, well, too late. Translated origin. And again, because of the nature of the hyperbola, as you translate the origin, you may want to make sure you set up your Cartesian plane appropriately to give you room to make such translations. Write this down if you would. X plus 2 squared over 25 minus y plus 4 squared over 16 equals 1. What is it that tells me that the origin has been translated, Quentin?
Something is being added to the x and y's.
Yeah, inside the square of the x and y, we've got something added or subtracted. Where do you think the origin is going to be?
-2, -4.
You guessed it. Again, not really anything new here, right? Just -2, -4. The transverse axis is still going to be which one?
X-axis.
Okay, the x-axis, because it's got the positive. The transverse axis is going to be how long?
5 each.
5 each. And the conjugate axis?
4 each.
4 each. And the focal length?
√41.
Square root of 41, which is approximately 6.5?
6.4.
6.4. And then the half latera recta, a little bit longer this time.
3.2.
3.2, so 16/5, which is 3.2. All right. Still not super long, right? We saw latera recta earlier, there were 9 and 8. 3.2 is not bad, but longer than the 0.8 we had last time. Still going to be a little bit of a tighter curve because the transverse axis is bigger. Anytime transverse axis is longer, we're going to have that bigger. Now remember, we're shifting back and down. And our axes themselves are a fairly good length, 5 in each direction, 4 in each direction. So I may want to shift my Cartesian plane accordingly to give myself a little bit more room in that third quadrant than normal. So slide the y-axis to the right a little bit, slide the x-axis up just a little bit, and give yourself a little bit more room than we usually would have. So I'm going to come over a little bit more here. I'm going to come up a little bit more here, making my third quadrant bigger than usual. That's a strategy tip. You're not wrong if you don't, but you could run out of room if you don't, and then that could be sad. And I guess it could become wrong if you didn't have room to complete the graph. A little bit more third quadrant space here. As we would do with all of our other conics, we're going to start by plotting the -2, -4 as my translated origin. And since my x-axis is transverse, I'm going to go ahead and draw a new x prime axis. Along the x prime axis, let's go
To the right and left 5.
right and left 5 to my
Vertices.
vertices. And we'll go up and down 4. And here we'll just do a little mark like that and like that to help me visualize the corners of the fundamental rectangle. So there's a corner, there's a corner, there's a corner, and there's a corner. Again, this one not nearly as, almost square, right? Not quite, but almost. It could be a square, just not. And draw your asymptotes through the corners. All right, from there, we need to go
To right and left 6.4.
from the,
Origin.
good, not the vertices out 6.4. I've had students like, there's not room to do this, Mr. Esky. I've had that happen on a quiz or test or something. No, from the origin, go out 6.4 to the foci. And then from there, up and down 3.2. The endpoints of the latera recta. And then from there, again, from the vertex, curve your way through. Curve your way through. Always use pencil, or in my case, chalk. And get something like that. Might be a little bit too much of a nosedive still there at my top. I feel like this side shaped up really nicely. I feel like that side didn't shape out quite as well. Questions though on the translated origin? Again, it's really straightforward. Now getting to this point is the fun one. So now let's talk about how to go from the conic to the hyperbolic form. Let's talk about going from the conic to the hyperbolic form when this origin has been translated. Conic to hyperbolic form when the origin's been translated. Really only one thing I want you to write down. Do it like the ellipse, but be careful with the negative. Do it just like the ellipse, but be careful with the negative. Do it just like an ellipse, but be careful with the negative. I feel like I'm a photographer or something. You know what a negative is? Mm-hmm. Yeah, okay, so you've used film before? All right. I'm only a few more years away from a class that has no clue what that means. All right, so with the ellipse, remember, we said we're going to group the x's and y's. So let's do that here, Quentin.
Negative x squared plus 36x in space, and then 4y squared plus and leave space, and we get -68
Perfect. Group the x's, group the y's, kick out the constant. Now, for each of my two groups, I've got to get a 1x squared and a 1y squared. So in the first group, I'm going to factor out
the 9, or negative.
A negative 9. And we've got to be oh so careful as we do.
So x squared plus 4x minus 4x.
That's one of the places we got to be really careful with the negative. And then here, it's a lot easier. And then, of course, like the ellipse, we'll complete the square.
Positive 4, then 1.
But it only looks like a 4, and it looks like a 1. Here's another time we got to be careful with the negative. It's a negative 36 and a positive 4. So since we put them on this side, we got to put them on that side as well. From here, the rest of the way should be really straightforward.
Negative 9 times x plus c squared, then positive 4 times 5 plus 1 squared equals 36.
And then from here,
Divide everything by 36.
to get?
So negative x minus 2 squared over 4. And then plus 5 plus 1 third over 9 equals 1.
And now we're ready to do the graph and the analysis from there. So 2 places to watch for the negative. Number 1, when you factor out, whichever of these 2 sets has the negative, make sure when we pull out the negative, we change the signs. And then when we get this number, it's not a 4, but it's also not a 36, but a negative 36. So be careful with that. The ellipse, we never had to worry about negatives. There were none. Here we have them, and we've got to be careful. So let's go ahead and graph this one, or at least I'll do it. You don't necessarily have to do it there on your paper. And let's just quickly finish the process. And we'll do the analysis mentally this time. Obviously, as you know from past experience, quizzes, tests, you'll be doing it on paper as the partial credit that makes up the test or quiz question. And I just realized I failed to account for my translated origin because I hadn't analyzed yet. We'll get a chance to learn the hard way together, potentially. All right, where is the origin?
2, -1.
2, -1. That's actually not that bad, right? So 2, -1 doesn't move me that far. I do need to draw a new y-axis because the positive is here, so the y prime axis will be drawn. All right, and then from the origin, we're going to need to go up and down 3 to the vertices, and side to side from the origin 2. That'll give me the corners of the rectangle, and that gets my asymptotes. And again, since I'm going y-axis, I'm going down. I get the skinnier parts, which is nice. It means I'm not going to have super long latera recta here. The focal length.
Square root of 13.
Square root of 13 is about 3.6. All right, so remember, you're not measuring from here coming down 3.6, but from the origin coming down 3.6. Just puts you a little bit more than half a unit past the vertex. And then what is the lattice rectum length? B squared over A. 4/3, or about 1.3. So about this far out. And we'll, ooh, that's parallel, isn't it? Yeah, that's definitely no good. Okay, so we'll do that instead. And something like that there. A lot of correcting little graphing mistakes, even for the teacher here. I'm no artist either, unfortunately. All right, and there we go. And that's what our hyperbola would look like then. The main thing, of course, is the algebra, and of course a little practice with the graphing never hurts either. Questions on this? All right, we've got time, I think, for one more, at least the algebra. Turn to page 252, and let's analyze 10b. So do just the analysis. We don't have time to graph 10b. Go ahead and do 10b there on page 252. Just the analysis. All right, origin?
-1, 0.
-1, 0. Transverse axis?
X-axis.
Length of transverse axis?
2 each.
Conjugate axis?
1 each.
Focal length?
2.2.
Square root of 5, which is about 2.2. Half latera recta?
0.5.
And so again, you're expecting a very tight hyperbola here. What are the tightest we've seen so far? Eccentricity about 1.1 is all we would get. So very, very tight hyperbola. Questions on this? All right, for homework this evening, going to have you do 4 hyperbolas. It's hyperbolas. 4 hyperbolas, page 251 to 252. Page 251 to 252, do number 1A. And then for practice with the translated origin, do number 10A, C, and E. Got a feeling you're going to ace number 10. Number 10, the letters A, C, and E. It was a dumb joke, but he chuckled at least. A sympathy chuckle. Jamie, hope you feel better. Missed you today. Have a wonderful rest of your day.